one short, and the first talk will be given by Daniel, who's going to tell us about how to improve jump point search. Thank you. Do you want this mic? You should use this mic.
Hello. So, hi, my name is Daniel. This is joint work with Alban and Grastien. We're both from NICTA and the Australian National University. So, our paper is about pathfinding. Specifically, we're interested in optimal pathfinding on a grid, such as this. So I'm sure you've seen grids 100 times before, but just to recap, so it's a discretization, 2D, a discretization of some kind of environment. The white cells represent traversable areas, the black cells are obstacles. Units move from the obstacle cell, from between traversable cells. So they can move straight at a cost of 1, or they can move diagonally at a cost of square root of 2. Okay. Very popular representation. It appears all over the literature. It appears especially in computer video games. So what's interesting about grids is it's surprisingly difficult in many cases to pathfind on a grid. So at least one of the reasons that it's surprisingly difficult to do pathfinding on a grid is because of something called path symmetries. So if you take a path on a grid, an optimal path, such as the one that you see here, in many cases it turns out that that path will have very many symmetric permutations, right? So what I mean by a symmetric permutation, if you think of a path as an ordered sequence of moves, so moves like go up, go across, you can, in many cases, get an exactly equivalent path by simply reordering those moves, right? So you go from the same starting location to the same goal location with the same cost, but now you're going through a different set of nodes. So, is it really such a big deal? Well, let me give you an example. So here is A star. This is a map that I use for testing. It's a synthetic map, but it's not too far away from what you might see in a typical video game. So we have a instance, the starting location at the top, the goal is somewhere down the bottom, the blue line represents the optimal path, and this sea of red is all the nodes that A star has to expand before it can find that optimal path. Okay? So turns out that if we start doing some symmetry breaking, some reasoning about the symmetries on the grid, this seemingly very challenging instance becomes almost trivial, right? So you can see very few red nodes over on the left. And we extract the same optimal path. So in 2011, we published a paper that deals with exactly this problem. And we describe an algorithm called jump point search. So the current paper builds directly on top of that paper, so I thought it would be good just to have a quick recap of what is jump point search, how does it work. So jump point search is an online algorithm for doing symmetry breaking during pathfinding. Okay, it's very simple. It reasons about symmetries using purely local information. So there's two sets of pruning rules, or there's two pruning rules, I should say, that jump point search applies depending on whether you are moving in a straight direction from the parent node or whether you're moving in a diagonal direction. And there's a bunch of stopping rules. So it's a recursive algorithm, right? We apply the pruning rules until we have to stop. So let me give you an example. Suppose we want to expand this node here, x, all right? So we read x and we look at the neighbors around it and we apply these pruning rules and we say, well, to each of these nodes that I've just highlighted in gray, okay, there is a better path or an equivalent path that goes from the parent to the node but doesn't go through x. Okay, so we immediately discard them. We say, well, there's a symmetric path, so we don't need to worry about those neighbors. So in this case, we have only one neighbor left. Normally, we'd be generating the neighbor, but in this case, we just recurse, and we apply the same pruning rule. And again, we have only one more successor that's not on a symmetric path, and we recurse, and recurse, and recurse, until we reach y. Y is an interesting node. So y has this neighbor z. Normally, z would be a node that we'd be pruning, okay? But because there's an obstacle, we're forced to consider it. So we say that z is a forced neighbor of y, and the recursion stops. And so we expand x, and we generate y as a successor, and we've jumped from x all the way to y, okay? Real easy. Same kind of thing happens when we're moving diagonally. So we're expanding x over on the right. We apply the local pruning rules. This time we have a bunch of neighbors left over, okay? Before we can recurse and step again diagonally, we have to make sure that there's no jump points located vertically or horizontally. So we recurse, we find nothing. We recurse horizontally, we find nothing. Now we can step diagonally, okay? And we do that again and again until we reach y, which has Z as a jump point successor if you go across horizontally. That's it. So that's jump point search in a nutshell. So the improvements that we have are 3. Okay? First of all, you've seen the jump point search reasons about symmetries one step at a time. So in this paper, we have something called block-based symmetry breaking, where we reason about sets of nodes and symmetries about them at the same time. So that leads to faster online search. We also have a method for doing offline jump point identification, right? So instead of looking for these jump points, you just store them in a database, you look them up during search, you go much, much faster. We also do something called jump point pruning. So this is also an online enhancement, and it allows us to discard some of the jump points that are currently expanded by jump point search. So how does block-based symmetry breaking work? Well, here's the same example I gave you just a second ago. Again, we're expanding node X. Again, the parent is off to the left. Okay? So normally, we would just be considering, as you saw, the node X and its immediate neighbors. But this time, what we'll do is we'll consider a set of nodes from the same row as X. All right? So here it is. Okay? So call that set BX. All right? So in the representation of BX, a 0 means that a node is traversable, a 1 means that a node is an obstacle. In addition to BX, we also take the set of nodes immediately above BX. So call this B up. Okay? And there it is. And we take the set of nodes immediately below BX. So call this B down. And what we do is we develop a function called forced. Okay? The implementation of forced is not that interesting, so I haven't included it here. It's a bunch of bit twiddling tricks. Okay? Shifting, anding, oring, stuff like that. What is interesting is the return value from forced. Okay? If there's a 1 in the return value, okay, it means that at that offset, there is a forced neighbor. So what the return value tells us is that we cannot jump past the first set bit in the return value, because otherwise we'd be jumping past a jump point, right? And so we don't want to do that. So we apply force to both B up and B down, and we take the results and we apply a disjunction together with the disjunction of Bx, and we derive something called a stop byte. Okay? So the stop byte, it's the same kind of idea as the return value from force, but this time we are also considering not just the position of force neighbors, but the positions of potential obstacles that are located along the row of Bx. Okay? So simply, what it tells us is we cannot go beyond the first set bit in the stop byte. Okay? So we have an operation here, find first set. It's a standard instruction found in the Intel micro instructions. And actually, we want to stop one position before. Okay? That's it. So that position is going to be a jump point. So this is how we reason about symmetries in terms of sets of nodes at one time. So, okay, that was a really simple example. In the implementation, things are a little bit more complicated. I showed you symmetry breaking moving from left to right. There's a similar procedure for moving right to left. We store the map twice. So we store it once in row major order. We store it again in column major order. This allows us to do up and down travel, okay, in exactly the same way. The example I used had 8-bit words. In the actual implementation, we use 32-bit words, so we can jump 32 steps in a single operation. Okay, bigger is generally better. We also played with 64-bit words in the implementation. In our experiments, it didn't make that much more difference. So we're directly improving the efficiency with which we find straight jump points. But we're indirectly improving the efficiency with which we find these diagonal jump points as well, right? Because you have all of these recursions vertically and horizontally when you're stepping diagonally. Okay, second improvement, offline jump point detection. This is really easy, right? For every node on the map, during a pre-processing step, we build a database and we say, all right, in the direction of every neighbor, find the jump point, okay? And we store it. And if there is no jump point, then we store the location of the dead end where we could go no further. We're not going to expand these nodes, but we need to know that they're there and where they're located. That's pretty much it. There's some extra details that I'm omitting. Mostly, they're a little bit boring. So Jump point search also has to consider the goal, and we have a simple reinsertion procedure so that we don't miss the goal because we're only storing information about nodes that are jump points or dead ends. It's really simple. It's constant time. It's not that exciting. So, just some words about the properties of this particular algorithm. In addition to being very simple, it's very space efficient, right? So you just need a linear amount of space. In the worst case, it takes quadratic time to compute this. That's a very loose bound. In practice, it runs in linear time. In our implementation, we store 2 bytes per label. So we have 15 bits to store the distance to the jump point, and we have 1 bit that says if it's a real jump point or if it's a dead end. Okay? So there's a bit of a trade-off, maybe you've noticed, about label size versus maximum jump distance. So we could use, for instance, 1 byte, right? We could use just 8 bits. But then we'd have to stop every 128 steps and expand because we can't go further with the information that we have. So this approach, you won't be surprised to hear, leads to some very fast pathfinding. You'll see that in a second. But we have some extra space that jump point search doesn't have. And if the map changes, then we have to update the database. So finally, jump point pruning. So normally, when a jump point search is expanding S and it's trying to move diagonally up, okay, it recurses and it gets to 1 and it goes up and it goes, oh, there's a jump point here. I have to expand node 1, okay? And then it expands node 1 and it steps just 1 step and it recurses across and it finds node 5 and it goes, oh, I have to expand 4, and so on. So what we'd like to do is to not expand these nodes like 1, 4, and 6. What we'd like to do is to keep on recursing until we hit a dead end. Okay, and just remember any of these nodes like 3, 7, 5, and 2 that we find along the way, and we generate those as successes. Okay, so we're increasing the branching factor, but hopefully we're expanding less nodes. And you'll see that it does in fact give a speed up. So it's really simple. It's purely online, but there's a trade-off. So experiments. We tested a bunch of these different algorithms. So JPSB, in the results I'll show you, refers purely to the block-based asymmetry breaking stuff. JPS Plus is purely just the pre-processing stuff. And then we have JPSB with the pruning and JPS Plus with pruning, all in C++. And we compare against the 2011 version of jump point search, and we also compare against the very recent algorithm that was presented at last year's ICAPS called SUB. So SUB is a pre-processing based pathfinding technique. It's really, really fast. Okay, it was one of the joint winners of the 2012 pathfinding competition. We test against 2 variants of SUB. One, SUB simple, is optimal. The other one, SUB 2 level, is mostly optimal. We use the source code from the competition, and we run 3 benchmark problem sets from the competition. The maps that are drawn from video games. So our work is very much kind of focused towards pathfinding in games. There's over 100,000 instances. All right. So search time versus jump point search. What you see along the y-axis is the improvement, number of times that we go faster than jump point search 2011. And along the x is the different algorithms that we're comparing against. So you can see on each of the benchmarks we do better. In the case of a JPSB, we do between 2 and 3 times faster in most cases, right, than the original jump point search algorithm. If we start looking at the impact that the pre-processing stuff has, you can see that we go up to 1 order of magnitude faster than jump point search. So that's kind of cool, because jump point search can be up to 1 order of magnitude faster than A star. So we're going hundreds of times faster than what's considered often state-of-the-art by the video games industry. So here's another comparison. This is versus SUB, versus the 2 variants of the SUB algorithm. So one of the winners, as I said, from the pathfinding competition in 2012. So over on your right, in each graph, you have SUB TL. That's the faster version of SUB. That's mostly optimal. And on the far right, you have SUB simple, which is always optimal. And on the left of each graph, you have the variants, different algorithms that we are using. So here, we're not looking at speed up, but instead just raw time. So this is microseconds, and there's a log scale. Okay? So what we find is that, okay, 2 interesting observations. JPSB is often competitive with sub-S. So JPSB is a purely online algorithm, right? And it's very often competitive with, in many cases better than, a pre-processing based, very fast, state-of-the-art technique. When we look at the database method, okay, so a JPS with a JPS plus versus a sub-TL, we find that, well, sub-TL is very, very fast, right? So for particular classes of instances, sub-TL does better. But on the instances as a whole, okay, JPS plus goes faster in 60–70% of cases on each of the 3 benchmarks. If you look at pre-processing, so over here you have, for each of the 3 different benchmark problem sets, we look at the amount of time needed to construct the database and the size of the database. I've just included some numbers for JPS Plus and sub-TL because I think they're more interesting. The paper has more details if you care to know. So main observations, both algorithms are very fast in terms of pre-processing time in most cases, right? In the case of JPS Plus, we never exceed a second. In most cases, we're done in a few hundred milliseconds. In some really bad cases, sub takes up to 20 seconds, okay? But they're both very, very fast. In terms of size, sub builds much smaller databases, so a factor of 2 to 3 smaller than a JPS Plus, but the databases themselves are not very big, right? They're typically a megabyte or a few megabytes, okay? The biggest ones we had were something like 21 megas. So very applicable to games where there's not many resources available. So, to wrap up, we study efficient pathfinding on a grid map. So we're interested in retaining optimality. And we extend a 2011 method that speeds up a pathfinding by doing symmetry breaking on the fly, okay? So we've talked about 3 different things. 1, we break symmetries over sets of states at one time. We give some enhanced pruning rules for jump point search, and we give some offline enhancements that can further speed up jump point search, okay? So we are, hopefully I've convinced you, very competitive with the state of the art. Yeah, that's about it. There's some interesting, in terms of future work, so there are a number of interesting looking problems. For example, I mentioned, you know, if the database changes, in the case of JPS Plus, we have to update it, we have to fix it. So it's not really clear how to do that, but it doesn't seem insurmountable, right? It looks like an interesting problem. So hopefully it's possible to just do a localized repair of the database and keep almost all of the benefits from having a database without having to recompute it every time the map changes, right? That would be very attractive. Yeah, that's it. Any questions?
We should have plenty of time for questions. All right, I'll ask one. So, here, I'll just steal this from you for a second. So, it's very clearly focused on grids, but if you wanted to extend it to a state space that wasn't two-dimensional, what kinds of obstacles would you have to overcome there?
So you wouldn't be using jump point search, in short. It's a completely different problem. So we've done a little bit of work at last year's ICAPS looking at non-grid representations, or rather, how do you do optimal pathfinding when you don't want to be limited to the points of the grid. But for just general terrain, I think most people end up doing something like navigation meshes, at least in video games, right? So this is where you try and build an approximation of the mesh that's actually representing the environment, so the detailed mesh, right, that has all of the rolling hills and stuff that you see in game demos. Yeah.
The 3D grid would have quite a bit of similarity with the 2D grid. Have you looked at that, and what type of issues would you see there? I mean, there is a lot of symmetries in there as well, right?
Absolutely right. So in a 3D grid, there are also very many symmetries, and jump point search looks like it could be extended, certainly, to this kind of environment. So there is no reason why jump point search is only applicable to square grids, for instance, right? You could adapt the rules, the pruning rules, to hexes, to texes, to even a 3D space, right? It's just a matter of changing the rules, changing the definitions so that you still have forced neighbors, right, that stop the recursion, right? I think that's it.